Well, I was asked, of course, due to the absence of the next speaker after me, to give a little bit longer speech this afternoon, right after lunch. And I thought, well, I could add more science stuff and probably put you to sleep after eating such a nice, well, but heavy lasagna. Or I can add more introduction, which maybe more of you would stay awake for. I did both. I'm not sure how far I'm going to get with the science stuff. But I'm going to make you sit through a little bit more introduction and also give you a little idea of our philosophy and the work we're doing in our lab. And to set the stage, of course, you have to take a step back and rather think about the more practical applications that were discussed this morning. Think about the size of the energy problem. Of course, you may know that today we're using energy at a constant rate of about 16 or 17 terawatts, continuous burn of energy, and that's almost equally distributed between industry, transport, and residential and service type of use. And not just electricity, of course, to point out that for transport, we need some type of energy storage and a fuel to use for this sector. And to put that in perspective versus a prediction of our energy use in the future, we can look at our expected energy use as a function of year according to the German Advisory Council on Global Change. And there we are in the year 2015. You can see we're using about 600 exajoules per annum. That corresponds to about 16 or 17 terawatts. And the makeup of our energy use today, as you know, is by most part fossil fuels. And unfortunately, our energy use is expected to grow, and by 2050, double, and by 2100, even triple based on the amount of energy that we're using today. And this is a problem, of course, with our CO2 production, and if we would like to mitigate the effects of climate change, the German Advisory Council on Global Change has advised that we follow a use of fossil fuels like this. So we have a huge gap to fill with renewable energies. How are we going to fill those? And at least one prediction from the German Advisory Council on Global Change is that the lion's share of our energy use by the turn of the next century is going to be solar energy. Now this is, of course, dangerous to make predictions because we don't know what will happen in the future. But since solar energy is by far our largest source of renewable energy, it seems like reasonable it can cover our energy demands up until the next century. So despite that, in Switzerland, our energy use may be different. Certainly we have a lot of hydroelectric. Perhaps other types of renewable energy will be very prevalent here. Regardless of that, we still need a way to store that renewable energy in a form that we can use later and potentially for a fuel. So the goal really of our work package 3 in the SECER is to take renewable energy, now it doesn't matter the form, and well, if it's sent to the grid, it can be used right away, but if we're not using it, of course, store that energy, and one way to do that is in chemical bonds in the form of water splitting. So we can take unused electricity and just drive an electrolyzer, splitting water into oxygen and hydrogen, effectively storing that energy in the chemical bond of hydrogen, which we can store in a tank or by other means, eventually using that in a fuel cell or even burning it for a gas turbine, finally returning that to the grid when we need it. Now, some of the drawbacks of this approach you may know. The round-trip efficiency is pretty low. A reasonable estimate for today's technology is about 20% efficient for electricity around this circle. If you burn the hydrogen, it can be a little bit higher, up to estimates of about 50% round-trip energy efficiency. But hydrogen does have advantages over other ways to store energy, for example, and that can be seen here on a plot that we've seen already, I think, this morning, a similar one, and I apologize for the quality of this graphic. It's not the best, but I like this plot quite a bit, which shows different energy storage possibilities here and rates them based on their power and the amount of energy they can potentially store. So batteries here are around in this area aligned with a short-term energy storage. However, technologies like compressed air energy storage are a little bit longer term, and pump hydro also longer. Well, hydrogen really is an outlier together with synthetic natural gas as a way to store large amounts of energy, as much as you want essentially, depends on how big your tank is, for a really long time. We don't have to worry about the degradation of our hydrogen. It can stick around for as long as we want to keep it in our tank. So certainly a diverse energy storage situation in Switzerland and across the world is going to use many technologies, but for the long-term storage, perhaps hydrogen will be very appropriate. In addition, hydrogen has quite another advantage over other storage techniques. For example, we can take our hydrogen and instead of going on the round trip, use that chemical energy to make chemical products. And indeed, we have a vision in our group especially to think about renewable hydrogen as really a keystone of a network of chemical transformations that will provide products like renewable fuels, longer natural gas, longer chain hydrocarbons, gasoline, and very importantly, ammonia through nitrogen reforming. Of course, today, we use the largest use of hydrogen is, of course, to make ammonia for fertilizers. And after our fossil fuels are gone, we're going to need a way to feed the people of the earth. Making ammonia fertilizers will be very important. Combined with CO2, perhaps metals for hydrogen storage, we can imagine kind of a complete cycle for energy storage and producing chemicals for value-added products, for example. So, overall, our work package 3 is really devoted to this idea of taking renewable energy and producing and storing hydrogen. And the different aspects of the different PIs and groups in our work package 3 are devoted to the different problems and parts of this situation. For example, Andrea Zuttel's working on hydrogen storage and electrolysis issues. Gabriele Lorenzi is working on a different way to store hydrogen effectively in a liquid formic acid energy carrier. Hubert Giraud is working on an alternative way to make hydrogen indirectly using a redox flow battery. And in our group, we're focused on looking at materials for this electrolyzer, looking at different types of electrode catalysts. So that is what I would like to speak to you about today, is some new results in our group on electrode catalysts. When it comes to using an electrolyzer to convert electricity into hydrogen through water splitting, there are two main camps. There are two main technologies that are available today. The well-established and traditional alkaline electrolysis, and the more new, I would say, PEM electrolysis, both of which have, of course, an anode and a cathode, which essentially do the same thing and overall convert water into hydrogen and oxygen. And they have different advantages or disadvantages for each. Of course, alkaline electrolysis is well established. It can be very stable in the long term, and it's relatively low cost. However, it doesn't work very well in a dynamic environment. In fact, they work the best if we can keep the current density the same and relatively high on these electrolyzers at all time. In fact, if we turn these things off and just let them sit in the caustic bath of the electrolyte, those electrodes are going to corrode. That's a big drawback for this type of technology. On the other hand, PEM electrolysis, which works in an acidic environment typically, is very good and very responsive to changing load from the grid, for example, and gives high gas purity as opposed to the alkaline electrolysis. As a disadvantage, there's a very high cost of the components, both the membrane and also the platinum used on the cathode are relatively high costs. Potentially, there's low durability as well. So both of these have advantages and disadvantages. They both could play a role in a system, hydrogen storage and production system, for constant current and constant hydrogen production and for more peak shaving type applications. And in both cases, we need to work on developing better catalysts. In this case, we would like to have catalysts that can be more stable in the caustic environments that are present in order to increase the ability to dynamically handle load changes. And in this case, we'd like to eliminate platinum as a catalyst altogether. So before I get to talk about the kind of catalysts that we've been working on in our lab, I want you to know a little bit of what the work that we do and how we measure these types of things in the laboratory. If we have a traditional electrolyzer like this with an anode and a cathode is producing hydrogen, and say, for example, we just would like to look at the reduction reaction, we just want to analyze what's going on this cathode, we'll use a potentiostat and vary the voltage that we put on this cathode as a function of a reference electrode and measure the current density. It's really simple. We just take an IV curve and we measure the current density accounting for the surface area of this catalyst. Now, here's a sample graph that we've made, and at this potential, 0 volts versus the reversible hydrogen electrode, this is the thermodynamic potential for hydrogen evolution or proton reduction to hydrogen. And any potential that needs to be applied after this represents the overpotential for our system. One of the goals of our work is to minimize that overpotential because any extra potential that you have to apply on your electrode translates to more money, obviously. So we want to have the smallest overpotential possible. Another metric that we use to quantify our electrodes is this Toffel slope. Following this Toffel model, we can solve for the resistance, first of all, to subtract the resistance, the IR drop in our electrode, and also fit it to a model to extract this Toffel slope. And this Toffel slope gives you an idea of how steep this curve is. If you ask the question, if I want to increase my current density by a factor of 10, how much more overpotential do I have to put on? And that's the Toffel slope. Of course, we'd want the Toffel slope as low as possible to indicate that we don't have to apply a lot more overpotential to get higher current densities. So typically, the data that I'll show you coming up is going to be overpotential and a Toffel slope. Unfortunately, the next graph is going to flip things up a little bit. And here's some results that came from a very recent perspective article from some big names in the field that are looking at new types of catalysts. And this is for water reduction in an acidic environment as a function of different types of materials that are used for the water reduction catalyst. And what you can note on this graph, unfortunately, this is indicative of the Toffel slope, but it's actually the inverse. What we'd like is this line to be as close to this axis as possible and have the highest slope because we've flipped the axes around. What you can notice is that the best performing catalysts are all platinum. And platinum has the lowest overpotential for the highest current density compared to any of these other catalysts. Now that's actually a drawback of these types of systems because platinum, well, it is fantastic as a water reduction catalyst, but it is quite rare in the Earth's crust. And many of you have seen this graph before, which gives an idea of the amount of platinum as a function of the atomic number. And platinum down here is one of the rarest metals in the Earth's crust. And today, actually, we don't need too much platinum for our electrode. Somewhere between 0.5 and 0.2 milligrams per centimeter squared is all we need, but still, if we're going to scale up hydrogen storage and production to the terawatt scale that we need, this may be a problem, especially considering the energy that's needed to extract platinum from the earth. If we look at the production of platinum as a function of year, in fact, because it costs so much money to extract platinum, in fact, some people think that we've already reached peak platinum. Peak platinum, you can type in Google, there are a few papers suggesting, in fact, it might not be worth it for us to extract more platinum. And that's because it takes a lot of energy to extract platinum. And here, from this paper, I show you that as a function of these different metals, common metals like iron, it only takes about 12 megajoules per kilogram to extract iron, 200 for aluminum. Fortunately not available for silver, but because platinum is so rare in our Earth's crust, it takes 1, 2, 3, 4 orders of magnitude more energy per kilogram to take platinum out of the ground. And that's because it needs to be purified over and over to get pure platinum. And while today we have cheap energy, platinum price is relatively low. As the energy price goes up, the price for platinum is going to scale accordingly. So that's something that we have to consider. So while it may be okay to make PEM electrolyzers now, and the other components of the device may be equal in price to the platinum, in the future we may be running into a problem with platinum. And that's why in our group, we try to focus on inexpensive materials and inexpensive processing techniques to make electrodes for this type of application. So what we'd really like, of course, is to have very inexpensive processing methods, for example, solution-based processing methods to be able to make electrode-type materials in a roll-to-roll type fashion for making the largest area for the least price possible. And of course, we want to use widely available materials. We have to have stable performance, and of course, high performance comparable to platinum, we hope. One material that has really emerged in the past, I'd say 8 or 9 years, being a promising replacement for platinum I should say, transition metal dichalcogenide type materials. And in this paper in 2007 in Science, it was really pointed out that these transition metal dichalcogenide materials, specifically molybdenum sulfide, can have a very high activity for the water reduction reaction, despite their fabrication from relatively available materials and inexpensive processing techniques being available. In this case, they found that the edge sites were very important to the activity for these catalyst materials, but these were made by an expensive type of chemical vapor deposition approach. Interestingly, these types of materials, these transition metal dichalcogenides, have many aspects which can allow solution-based facile processing. Of course, in general, these types of materials come from a larger family where molybdenum or tungsten can be combined with any of these chalcogenide atoms to make these type of layer materials that have many important properties that are useful in material science. They're ultra-thin, soft, and high strength, and high charge carrier mobility. We have high charge transport in these materials. They're used for electronics like field effect transistors, even in batteries, for semiconductor applications, for catalysts, and also for lubricants. That seems sort of weird. Why do you think they're lubricants? Well, in fact, because of the crystal structure of these materials, we have only van der Waals interactions between these types of layers, and there's not a strong covalent chemical bond. These layers can slip right past each other, just like graphene, for example. That makes them good, obviously, as a lubricant, and it also means that they can be exfoliated into single-layer sheets. Now, typically, if you know the field of 2D materials, you know that this is done most commonly with the Scotch tape approach. This mechanical exfoliation, where essentially we can just take our bulk material, we can buy some molybdenum sulfide from Sigma Aldrich or a less expensive type of vendor and put it in between some Scotch tape, pull it apart a few times, and eventually we'll be left with perhaps a monolayer of the material, which maybe we can get onto our substrate and measure the catalytic or electronic properties of it. And in fact, we can see by AFM, we can get these monolayer type materials. This is from a Nature Nanotech paper that came from Andras Kiss group at EPFL, and measure, for example, in this case, charge carrier mobilities that are extremely high, suggesting that these materials could also be used as semiconductor materials for transistors in inexpensive types of semiconductor devices. But what we want to do with them is take advantage of this exfoliation property and use that to very inexpensively process catalytically active electrodes. So how can we do that? Well, a good thing about these materials is we can, again, buy the bulk material, put it in some solvent, shake it up a little bit using an ultrasonicator, and we can actually split these layers apart, dispersing them in the solvent. In fact, this was reported by Coleman in 2011 in a science paper, and it has become a very important result that can be done with lots of different types of layered materials. Unfortunately, if we try to actually take this solution and process it into a thin film catalyst or electrode, we run into problems. As we remove the solvent, for example, by spin coating or another approach, what happens is the layers, of course, restack. And we get, unfortunately, aggregation, which prevents homogeneous film formation. So this is a definite problem for making consistent and high-performance electrodes with this material. Now, very recently, our group developed a way, well, actually found a special type of surfactant here, this trichloroalkyl cello group, which can, in certain cases, depending on the treatment, attach to the surface of these transition metal dichalcogenides, in this case molybdenum sulfide, and really prevent the restacking of these sheets. And that can be really clearly seen when we look at the XRD, which of course measures the distance between the planes using X-ray diffraction. And while our standard material, a control material, exhibits a restacking, which shows a peak here at about 14.5 degrees, when we apply either the BTS, the HTS, or the OTS, we see almost a complete elimination of this restacking and the formation of a new peak corresponding to an expanded restacking of our molybdenum sulfide. And while thankfully that expanding restacking matches very well with the length of the chain that we use. So for the OTS, for example, the longest chain, we have indeed the smallest diffraction peak, smallest 2 theta, which corresponds to the largest stacking distance. So it's consistent in that respect. Our Raman, I'll talk more about Raman in a second, also gives indication that we're separating the layers. Importantly, we found that our solutions, when we treated them with these surfactants, were stable for days, weeks, months. Now we've had them in the lab for a few months, and they're still completely stable and dispersed. It means that we can start to think about making some reasonable films with these simply solution processed materials. I'll give you an idea of what these materials look like. I show you the electron microscopy here. Here we see some flakes of our molybdenum sulfide, sort of aggregated a little bit. It's hard to keep everything separate when you're doing a TEM sample, but you can get an idea of the size of the flakes that we're working with here. And they look a little bit like the things that we saw in the science paper already, when there's sort of triangular and layered type material. So we hope that these have a lot of edge sites that could be conducive to having high catalytic activity. In addition, the centers of these flakes have good crystallinity, which we hope could help facilitate charge transport to those edge sites. Well, still film formation was a little bit difficult with these samples. We were able to make thick films using a special drop casting technique and letting the solvent evaporate very carefully. And you can see here they all look very black using the different surfactants. And while these films are quite thick, we can put a top electrode on them and measure the charge transport through them, but I can tell you that the conductivity or the charge mobility that we measured is actually quite poor, probably because we have to hop between all of these different sheets to get all the way up to the electrode. But more importantly, we see a trade-off between the length of the carbon chain here and the electronic properties. So in this case, the BTS, which is a very short chain, we found actually performed the worst as far as the electronic properties, and this is probably because the shorter chain doesn't disperse the sample, disperse the flakes as much, and I don't show it here, but we have larger aggregates and void spaces in that sample. Whereas the OTS now is too long and acts as an electrical insulator to stop charges from passing from one flake to the next. The happy medium here is the 6-carbon HTS type of material, and we proceeded on with this to try to make thinner films on conductive substrates to measure their catalytic performance. So here are some films that we've made as electrodes to reduce water into hydrogen, and we've used a standard procedure that's published to make electrodeposited molybdenum sulfide, and also used spin coating with annealing at a low temperature to produce our films here, which are relatively homogeneous and easy to produce. And in fact, they work to reduce water pretty well. Now, here's these IR-corrected JV curves that I mentioned before. And of course, here is the platinum standard. So this is what we'd like to get to eventually. Here's the electrodeposited molybdenum sulfide following a known route. And our samples, which were prepared by a simple solution-based exfoliation, either using a lithium intercalation or two different solvents here, NMP or dichlorobenzene, performed reasonably well compared to the standard molybdenum electrode deposition, but not as good as it. And in both cases, in all cases, they're still far away from the platinum. We look at, in detail, both the overpotential and the Toffel slope for these different types of molybdenum sulfide that we've made. And there's a lot of data here, and I don't have time to go through all of it, but the important thing to note is that for the electrodeposited sample, which is in red, it performs very well, very close to platinum under acidic conditions, but further away in basic conditions. However, our solution-processed samples actually perform closer to the electrodeposited sample in basic conditions, which suggests that perhaps our materials would be more useful for this alkaline electrolysis, but we have to investigate more the long-term stability of them in the basic conditions. But it begs the question, what's the difference between the performance of these three different exfoliated in the NMP solvent, exfoliated in the DCB, and also this lithium-type exfoliated sample? And to get an insight into that, we did some analysis using Raman spectroscopy. And if you don't know what Raman is, I can tell you very quickly that it's a way to measure essentially forbidden phonon modes in a crystal material. And the signal that you observe from your sample is correlated somehow to the quality of that crystal, defects, certainly the crystal phase that you observe. We noticed something striking about the performance or the crystallinity, the Raman response for these materials as a function of the processing technique. While our NMP exfoliated material gave a very strong signal suggesting it's quite crystalline, that diminished as we moved to a dichlorobenzene or the lithium. Finally, for the electrodeposited material, absolutely no Raman peak was observed at all. And if we look at the performance again, here's the same graph that I showed you before, we can see that this correlates very well with the activity. In fact, a higher crystalline material performs poorer in this case. And in fact, this aspect for these materials is well known, but before we never had a way to really vary quite systematically the amount of defects, for example, in the material. So our ongoing studies, we hope to elucidate exactly what the defects are in these cases that are catalytically active for this water reduction reaction and enable us to exploit them a little bit more. Okay, well, I still have 15 minutes left. That's great, because I've added more slides. Let you all get a little bit of a break. Is it hot in here? I'm going to shift gears a little bit, but go back to this same topic, which is, of course, we'd like to take renewable energy and use it to store that renewable energy in the chemical bonds of hydrogen. And we can do that, like I said, using electricity from the grid, using solar cells, for example, and directly taking solar cells and splitting that into hydrogen and oxygen. Now, in general, this is a great, fine technique. Why not? We can do this today. We can use technology available today, a PEM electrolyzer, silicon photovoltaics, and we can do this. So why aren't we doing it? Why aren't we doing this all over to store electrical energy? The answer is simple. It's just economics. We know, of course, that this approach is not limited by the price of the electrolyzer. It's limited by the price and the availability of the photovoltaics that we're going to use to convert the solar energy into chemical energy. There are some other drawbacks, but overall, we can already do this today and produce hydrogen for the price of about $10 per kilogram, which is not so bad. But if we use other methods to produce hydrogen, for example, steam reforming of natural gas, we can produce hydrogen for about $2 or $3 per kilogram. So there's absolutely no economic incentive for us to use this technology today. And this is even more important when we look at the amount of energy that we'd like to be able to get out of this approach based on this prediction, suggesting that we need a few terawatts of solar energy by 2050, and probably about 12 or 15 terawatts, or even more, by 2100. Well, one good thing about this is that the price of silicon photovoltaics is dropping dramatically. And many of you may have seen this curve before, but this is what's called the technology learning curve. And what it shows is the price per of electricity produced by silicon photovoltaics as a function of the amount of photovoltaics that we produced, a cumulative production. And of course, as we develop technology, we get better at making these silicon photovoltaics, the price goes down and down. And today, depending on your electricity market, actually we're at parity with electricity produced by traditional grid techniques like coal burning electricity. Again, depending on the electricity market. And we hope that we can continue making it cheaper to install more and more photovoltaics, and maybe this problem will actually have a reasonable solution, and we can fit all of that extra terawatts of energy that we need using just traditional silicon photovoltaics. To get an idea of whether you think that might be possible, we can look at how silicon photovoltaics have grown over the past few years. Now here, this is a few years old. This came out in 2013, but it shows that every year, now we're putting in about 100 or more gigawatts of energy using silicon photovoltaics. And that's quite impressive. This growth rate, hopefully by 2018, will be up to almost a half of a terawatt of energy from photovoltaics. But if we put this on the scale of the energy demand, things don't look so great. Here's the target that we'd like to meet for solar energy by 2050 from the German Advisory on Council on Global Change, which I showed you before. And it's quite difficult in my mind to imagine any sort of extrapolation of this technology to sort of meet that target, right? this might be possible, but we have to radically change our production of silicon photovoltaics. And that's difficult because it takes a lot of energy to make silicon photovoltaics. We have to take the sand, we have to convert it completely to silicon chloride and deposit it and refine it and purify it and crystallize it. So instead of doing something like this, another possibility is to develop a new approach that could potentially be less expensive. Here we can imagine a direct solar to chemical energy conversion using a photoelectrochemical cell. So instead of using a silicon semiconductor coupled with an electrolyzer, we can use a photopotential developed directly by a semiconductor liquid junction to split water into oxygen and hydrogen directly. Now, this approach potentially, as it uses less components, can be less expensive, in fact, a lot less expensive than a traditional type of approach. But that depends on the components that we use. In fact, the economics of this type of approach are quite well studied by other groups, and I can tell you about that now. If we can imagine using this direct photoelectrochemical type of device, which splits water directly with sunlight, something that looks like this. We know we need a photoanode and a photocathode, which is fine. We need two electrodes anyways. Both of them, in this case, are going to absorb different parts of the solar spectrum and produce bubbles of oxygen and hydrogen, which in an integrated system could look something like this. We'd have troughs of electrolyte here and collection of the gases at one point. Now, if we imagine a system where the net production of hydrogen was 1,000 kilograms per day on average, and we had an efficiency of solar to hydrogen of about 10%, then assuming a cost of our cell of about $150 per meter squared, and a lifetime of 10 years, we could produce hydrogen for about $10 per kilogram, that same price that we can get with silicon photovoltaics plus an electrolyzer. But you'll notice that I had to assume a relatively low price here compared to the $200 or $300 per meter squared of silicon photovoltaics. So in any case, our technology has to use materials that can be less expensive than silicon photovoltaics. Indeed, if we can even reduce the cost further, we can save a lot of money on the price of the hydrogen. And this is a tornado plot which shows the sensitivity of the cost based on these different scenarios published by Jaromil's group here in Energy and Environmental Science. And if we can imagine the cost of our cell going down to $80 per meter squared, already the cost of our hydrogen produced cuts, well, almost in half. That's not so bad. If we can further imagine an even less expensive type of PEG cell, this price could march down, and hopefully we could even meet a cost that was commensurate with the price of hydrogen produced by steam reforming of natural gas. But to do that, we need to use this approach of using very inexpensive processing techniques, roll-to-roll type compatible processing techniques, and use widely available materials, but still get high-performance energy conversion. And in our group, we've spent a lot of time developing these types of oxide materials as a photoanode. For example, iron oxide is a very promising material for water oxidation because it's really stable under those conditions. We've demonstrated even overall full devices using this approach with iron oxide or tungsten trioxide, which were very good with stability, but instead of using a photocathode, we had to use a dye-sensitized solar cell here as the second electrode, unfortunately. And that dye-sensitized solar cell, some of you might be familiar with this technology. It has an encapsulated iodine or cobalt-based electrolyte that, of course, we can't let it leak with the water. We have to protect this. And that might be too expensive, really, to meet maybe our goal of having a $10 per meter squared type device. So more recent work in our group has focused on the idea of, can we develop a semiconductor photocathode to replace that dye-sensitized solar cell, essentially making a device that would be like this, an artificial leaf. Now, this artificial leaf was published by Dan Nocera and his group a couple years ago, and it uses a silicon triple junction here, which is certainly not inexpensive, way too expensive for this approach. But the concept is really there. If we can have a very simple type of device and we can just place this into the water and it can evolve hydrogen and oxygen, well, potentially that can really be a game changer in the idea of hydrogen production and storage. And so we're developing now currently some of these different materials. And in the last 5 minutes, I'm going to complete the story with these transition metal dichalcogenides and tell you about our work with tungsten diselenide. So tungsten diselenide is, again, just like molybdenum disulfide, one of these layered type materials, and has been investigated for actually quite some years in photovoltaic energy conversion and even in photoelectrochemical hydrogen production. And this is from Nate Lewis and co-workers. And by the way, if you're going to be around tomorrow, Nate Lewis will be here giving a talk, and I highly recommend that you come and see him if you can. He's a very dynamic speaker, and maybe he'll even talk about this work. I don't know. But our idea was to use our method to make very inexpensive electrodes of transition metal dichalcogenides with this material and see if we can get some solar activity for water reduction. Unfortunately, using the methods that we've developed so far, we have very poor film formation. It doesn't look good for semiconductor activity. So we took some inspiration from the literature, which uses simple types of self-assembly at 2D liquid-liquid interfaces, and developed a method to make very homogeneous thin films of our separated flakes. And on the next slide, I'm going to show you a video. Here, hey, it works. Great. Here we have a standard Legmer-Blodgett type of film formation, and our special self-assembly using a liquid-liquid interface. We use ethylene glycol and hexane, and here we're going to put our dispersion of transition metal dichalcogenide flakes. In this case, it's tungsten diselenide. We're going to put it on top, and hopefully, we're going to get a self-assembly of these flakes and some nice alignment. You can see that the flakes float on top of this liquid quite well, and here they're lining up. But we know, based on the evaporation of this hexylamine, which we're using, they're aggregating quite significantly. In this case, we're putting this on, but because the solvent quickly goes into the hexane or the ethylene glycol, the flakes have to self-assemble at that liquid-liquid interface just due to energetic conditions. And we'll have a less material that's needed to completely cover the liquid-liquid interface in this case, suggesting that we have good alignment of these flakes. In fact, if we look at the SEM here, we see we have almost a monolayer of these flakes on top of our conducting substrate and a relatively homogeneous film formation compared to this case, where we have big aggregates when we use this traditional approach. Now, finally, we leveraged this approach to develop a way to put this onto electrodes, and here I'm going to show you another video. We think that this can be actually used in a roll-to-roll type of a system, but I show you it here just in a batch, and right here is the interface between the ethylene glycol and the hexane. And you can see we inject the dispersion of the transition metal dichalcogenide. Remember, we got this just by shaking up a solution of material that we bought from Sigma Aldrich. Then we remove this top phase just with a syringe. And finally, we remove the bottom phase out of this frit. It looks quite nice. We have to take the sample over to a hot plate just to evaporate that solvent, but after a few minutes, we have a film that looks fantastic. We can put this on flexible substrates, so we can do roll-to-roll type processing with this, we hope, and we can also scale this up to relatively large size. Now, because these are exfoliated flakes, they're not perfect, but we have pretty good alignment of the flakes in this two-dimensional direction, but we have some void spaces between the flakes due to their irregular shape. Now, just to make a long story short, we investigated these electrodes for their activity in the direct solar to hydrogen production, and even without any catalyst on top, we saw some activity for both of these films made by this special 2D self-assembly or by this traditional aggregated type approach. In addition, we can show by looking at the different wavelengths of light that this photocurrent that we see it directly comes from the absorption of light by our transition metal dichalcogenide. And finally, after we put a catalyst on, now I have to admit we do have to put platinum on these, a very small amount, just to get this water reduction reaction to go better, because the tungsten diselenide isn't a great catalyst itself, but we can get about 0.5 milliamp per centimeter squared, which is not so bad considering the way we made these samples, and a stable performance over, well, minutes to hours for these samples without any problems. In fact, we haven't tested them for longer just because we've been too lazy, probably. Finally, we can make some statement about the importance of the self-assembly layer that we've made here as opposed to the aggregation. But I won't spare you the details because it's a little bit technical. So with that, I think my time is up, and I hope today I've showed you a little bit about how hopefully we can take renewable energy, store that energy in the chemical bonds of hydrogen, and convinced you that to do that, we need technologies based on widely available materials and inexpensive processing techniques if we ever want to hope to get to this terawatt scale of energy conversion. Also, I hope that you saw that these transition metal dichalcogenides, these 2D materials, are quite promising due to their ability to be inexpensively processed. Drawback, of course, is that we need higher performance. It's in red because it's to do. We need to still understand how these materials work in order to increase their performance towards the more expensive and traditional approaches. So with that, certainly I have to thank everybody in our work package who are working on different aspects of these problems, and people in the group who are working on these projects, especially Florian and Victor, who are working on these catalysts for hydrogen reduction and are here today. And for funding, thank you for your attention.